Welcome everyone to our Tech Excellence Conference session, Modern Software Engineering, Building Better Software Faster. And we're really excited to be joined by Dave Farley. Dave is a pioneer of continuous delivery. He is a thought leader and expert practitioner in continuous delivery, DevOps, test-driven development, and software design. Dave is also the managing director and founder of Continuous Delivery Ltd. He is the author of two best-selling books, which you've probably already heard of and read, Continuous Delivery and Modern Software Engineering. And he also hosts the Continuous Delivery YouTube channel. So we're really looking forward to learning from you, Dave, and now handing over to you.
Great. Thank you very much for the introduction, and good morning, good afternoon, whatever time zone you're in. I'm interested in kind of the ideas of what things are durable, what things can we rely on being true and apply to doing a better job. And I think that if we can identify those things, we can think of that in terms of software engineering. And so I know that the term software engineering is probably somewhat contentious in software terms, but I'd like to convince you that there's something important here and something worth considering. So let's start with what is engineering and talk a little bit about what the role of engineering in general is a little bit, but certainly with a strong look at applying those sorts of ideas to software. And then talk about some foundational principles that I think are guide rails that we can use to always do a better job in software development. And then we're going to explore those 10 principles for software engineering with some examples from the real world, not from software, but some examples from software too. And then look at what happens when we apply those kinds of principles to some simple code. So let's start off with the first of those. What is engineering really? And I think we often mistake this when we talk about it in terms of software. But in other disciplines, engineering is really just the stuff that works. I think it's reasonable these days, at least for modern engineering, to describe it as the kind of practical arm of scientific rationalism. We're going to apply scientific style thinking to solving practical problems. But software is a difficult problem. So what are the things that work for us? I've been talking about ideas like software engineering and what it should mean for a little while now, and as a result I've got involved in quite a lot of conversations about bridge building. It usually starts with somebody saying, yes Dave, that all sounds very well, but what we do isn't bridge building, is it? And of course what we're doing isn't the same as bridge building, but I think that what people mean when they say that is also not true of bridge building. I think this is mistaking software engineering with manufacture, and that's not the same thing at all. So when we do start thinking about different engineering disciplines, they're not all the same. Bridge building is not the same as aerospace engineering, which is not the same as chemical engineering, which is not the same as civil engineering, and so on and so on. And so one thing that we can be fairly sure of is that software engineering, whatever that is, will have some unique properties of its own. It will be different to the others. But I think they all share some principles, and there's some importance here in these ideas. In the rest of my talk, I'm going to be taking examples from three other industry sectors: space rockets, aviation, and car manufacture. And I might be talking a little bit about Lego for a while as well. So what does all this mean to do? What has this got to do with the job of creating software well? So I think asking the question what we mean by engineering is a good one. My working definition, and the definition that I'd like you to keep in mind through the rest of my talk, is this: Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. And I think that that's quite a concise description, and all of those words are correct and you can't do without them, really. So I think that's a good working definition of what it is that we're talking about. To put it more simply, though, engineering is how we solve the hard problems. If we want to create a COVID vaccine, build a large Hadron Collider, or send people into space, it's engineering that does that for us. If we want to build the computers that we're relying on for this talk, or even the chairs that we're probably sitting on, that's an engineering problem too. Our society is built on engineering. I would say that engineering is the foundation of our high-tech culture, really. Here's a graph, and this is not deeply accurate, but an approximation of technical advancement over human history. Human beings have existed for something like 200,000 to 300,000 years. So the timeline goes a long way further off to the left here in this diagram. But as you can see, something important happened around about 1600, and that triggered this kind of explosive growth. And what happened there was really the invention of science. So there's a connection here between technological advancement based on engineering and science. Here's another graph. This is a graph created first by Buckminster Fuller, who was an IBM research fellow. And he got interested in the rate at which knowledge, all human knowledge grows. And he estimated that in 1900, all human knowledge was doubling every century. By 1945, it was doubling every 25 years. By 1982, when Buckminster Fuller first did this research, he estimated that knowledge was doubling every 12 to 13 months. And somebody, since Buckminster Fuller's death, redid this work and predicts that knowledge now is doubling every 11 to 12 hours. I'm not entirely sure that I believe the last one, but even so, I think we'd all recognize that the pace at which humanity acquires knowledge is growing, and is growing fast. So science happened somewhere back there, and the invention of computers and software happened here. A lot of knowledge and understanding these days is generated by or through the use of computers. So what's engineering really for? And I think this is another place that we tend to get a mistake. Engineering is not about identifying a perfect, precise solution. Rather, it's for this. It's to stop us doing the bad solutions. It's to stop us making mistakes. It's to rule out bad ideas and to guide us in ways that allow us to choose from a multitude of good ideas. We often think, as I've already alluded to, of engineering in these sorts of terms, and that's a category error. That's a mistake. So the first thing is that that's not engineering. This is manufacturing, and these are production lines. And the idea of a production line is to do things perfectly, repeatably, over and over again. That's not what engineering is about. Engineering is about solving practical problems. So this is never our problem. And it's never our problem for an interesting reason. So uniquely, really, digital assets in general and software in particular, the way that it works is that we capture and identify some collection of ideas, and then we encode those ideas into a binary stream of data. And then at the push of a button, we can perfectly recreate that binary stream of data as many times as we like. And we can do that essentially for free. This is a zero cost activity, essentially, because we can perfectly reproduce any binary stream of data. So the systems that we produce, we don't have a production problem for those, we have a creation problem. Our discipline is very different from a problem of production. So I think that one of the outcomes of that line of reasoning is that engineering is really about exploration and discovery. So I think that software development is also about exploration and discovery. So I think that they are a great match. So let's talk a little bit about the stuff that does work when we start applying engineering thinking to software development. I want to caveat this before I start, in that none of the ideas that I'm going to present to you are going to be new to you, I'm sure. But I want you just to think a little bit about what they mean if we always work in ways that prioritizes and prefers these ideas. And that's what I'm really recommending. So let's start with the first one. We need to be, if this is a discipline of exploration and discovery, we need to become world experts at optimizing for learning. We need to be good at learning and have effective techniques that allow us to learn well. But we build these complex systems, so we also need to be able to be good at that as well. So we need to also optimize for managing the complexity of the systems that we create. So both of those groups of ideas lead us to start thinking about, okay, so what is it that's going to help us to learn? What is it that's going to help us to manage complexity? So here are my 5 principles for optimizing for learning. We want to work iteratively, experimentally, be feedback driven. We want to make incremental progress and base whatever we do on empirical learning. Engineering is importantly an empirical discipline where we learn from the reality of the use of the systems that we create. So let's look at each of those ideas in more detail with some practical examples. So this is a picture of the Wright Flyer. This first flew in 1903 and was the first heavier than air, man-carrying, powered, controllable aircraft to fly. And all of those qualifications are necessary because there were versions of aircraft that did one or other of those things before the Wright Flyer. But the Wright Flyer was the first aeroplane to bring all of those things together, and so practically to really work. And in the days when the Wright Flyer was invented, and for the 2 or 3 decades afterwards, experimenting with airplanes like this was incredibly dangerous. Nearly all of the aviation pioneers were killed by the aircraft that they were pioneering in. Including one of the Wright brothers, who was killed by an aeroplane very like the one in this picture, not very long after this picture was taken, really. So what happens in engineering is we iterate over long periods of time when we're talking about physical objects like aeroplanes. This aeroplane is a Douglas DC-3. This was the first, probably the first obviously recognizable form of passenger aircraft. There were passenger aircraft before this, but they looked much more old-fashioned and very different to a modern passenger aircraft. Here, many of the common factors of a passenger airplane are present in this design. This was much safer than the kinds of things in the Wright brothers picture, but it was still prone to bad weather, and still people were dying flying in these things at the time. It was still a slightly risky endeavor to take an airplane ride. So what happens is that we carry on iterating and learning from the mistakes, sometimes learning from the fatalities, and we end up with something like this third picture. In 2017, the equivalent of 2/3 of the population of the planet flew in commercial airliners, and there were no fatalities. That was the first year that happened, but that was a function of working iteratively in controlled steps and learning from the mistakes after each step. So iteration is a powerful feature of all engineering, really. We have some advantages in software because we can iterate more quickly, but the idea is the same. Iteration is incredibly important as an idea. It sounds in some ways less rigorous, but it's not. The alternative is really getting all the answers perfectly right before we start. But in iteration, it's more powerful than that. If we've got a goal of some kind that we'd like to hit, then all we need is that we need to start somewhere, anywhere, and then establish a measuring stick of some kind, a fitness function that will determine whether we are closer or further from the goal. Now, if we want to, we can iterate at random. We can be informed, if we like, we can make guesses that we think are more likely to be successful, but we could just start at random and then start measuring what goes on. If we're further from the goal, we discard that step and then we try another. And if that gets us closer to the goal, we keep that step and move that as the next starting point and then repeat. With this process, this very simple process, really, then we can certainly hit the goal. It might take us a few steps. It might take us many, many steps, but we can achieve the goal. And that's how we solve the hard problems. That's how science works. That's how engineering works. That's how machine learning works. That's how evolution works. This is a much more powerful way of solving a problem. Next in my list is feedback, and feedback in this little model is obviously the measures that we take on our fitness against our fitness function. They give us feedback on whether we are moving in the right direction or not. But another way of thinking about this is, let's imagine that we've been asked to balance a broom. So we could do this in two ways. So we could decide to do the waterfall way of balancing a broom. So we could carefully measure the broom. We could identify the center of mass. We could remember our physics from school and remember that if we want to balance something, then what we need to do is that we need to align the center of mass with the point of contact of the thing that we're trying to balance, and then very carefully position the broom. And that's probably not going to work. The broom's going to fall over. And the reason it's going to fall over is there's probably only one perfect solution to this. And the only way to hit that is to make sure that we balance the broom absolutely perfectly in that one position with no tiny impulse that's tipping it one way or another before we let go. And all of this stuff, it's incredibly difficult to be able to get that to work. It's possible, but almost impossible. So the alternative to this, which I'm sure is what was going through your heads when I talked about balancing brooms, is that we do this. We get the broom, we stand it up, we put it on our hand, and then as the broom starts to tip, we correct for it. We gather feedback. We determine which way it's tipping, and then we correct. That's a much more powerful approach. That's a much more flexible approach. If I'm balancing a broom on my hand like this and somebody comes and pushes me from the side, I can make a bigger move and rebalance the broom and carry on balancing the broom on my hand. This is a very resilient way of solving this problem. It may seem less rigorous once again, but actually it's not. This is how spacecraft fly. A spacecraft does exactly this. It has sensors inside the rocket that determine how it's tipping, and then it can move, it can point the engines in different directions. They call it gimbaling the engines. So they can swing the engine to correct for any tips that they don't want to happen. And they can keep the rocket going in the direction they want it to go in, and they can even these days bring it back and land it. Next in my list is working incrementally. This is a picture of the first module of the International Space Station. And then incrementally, they built this up launch by launch, component by component, until we get to the amazing device that's often quoted as being one of the most complicated machines that humans have built. I think those people that say that haven't looked at the internet, but apart from that, it's a pretty complicated machine. And I guarantee you that when they launched that first module into space, they had some approximate idea of what the future of the space station would look like. But I also guarantee you that the end goal, the actual realization of the space station isn't precisely the same. It's changed over time, and that's partly because new technologies have come into play, new ideas have come up, new spacecraft have been created since then. So there have been lots of changes over time, and that is a version of incremental development. We build things in modules, and we use the modules in different and flexible ways. Next in my list is working experimentally, and one of the bits of feedback that I get when I say this is that being experimental is scary because it implies that we might fail. Well, yeah, but if we don't take the risk of failing, we're also not going to succeed. Experimentation is how we learn. It's how we move forward. It's how we do new things in a controlled way. So how else can we make progress if we don't approach things from an experimental stance? So if we want to be experimental, we need to think about ideas like controlling the variables, limiting the scope of our experiments so we can do that safely and not risking the whole company or the whole endeavor with one great try. Aeroplane designers have worked experimentally in this way for a very long time. If you want to create a new aeroplane with a new type of engine, then you don't just build the new aeroplane and new engine and go flying. What you do is this. You start off with an old aeroplane with an old engine, and then you replace the old engine with the new engine, and you get very brave people called test pilots to go and fly it. Sorry, pressed too soon. Then you go and get test pilots to go and fly it, and if they come back alive, then you know that engine's working well enough. Then you move on and you get the new aeroplane and you bolt on an old engine. You go and fly that, and if they come back alive, you say, well, that's worked okay, so now we can try the new engine with the new airframe. And aviation has made progress moderately safely following this practice for a long time. Each of these experiments is a little controlled experiment, trying it out, de-risking, trying to limit the blast area of failure so that we're not likely to kill the test pilots just by putting them into a machine that we've never tried before. Last in my list of optimizing for learning is the idea of empiricism, working empirically. Here's another aeroplane. This is the first production jet aircraft. This was built during the Second World War and is an airplane called a Heinkel. Now, I'm an aeroplane nerd, which is why I'm showing you lots of pictures of airplanes. And as such, I can tell you that this is what's called by pilots a tail dragger. That's because there's a little wheel at the back that drags along behind the aeroplane, and the airplane is balanced on the big wheels at the front. And if you look at nearly all of the airplanes before the Second World War, they look like this. And if you look at nearly all of the airplanes after the Second World War, they don't. They look different to this. And the reason for this is kind of obvious when you stop and think about it. All of those earlier airplanes before the jet engine had a big propeller on the front. And so if you want to build an airplane with a big propeller, you need to make room for the big propeller so that it doesn't bump into the ground while the airplane's on the ground. So they tipped the nose up by organizing the wheels like this. So that's what the designers of the Heinkel did. And then they went and flew the airplane, and it flew very well, but it melted the runways. So they learnt their lesson empirically. They corrected this problem. They moved the big wheels a little bit further back, and they replaced the small wheel on the tail with a small wheel on the nose of the aeroplane, but on a stick, so that the aeroplane stood horizontal on a kind of tripod. And that's basically the layout of nearly all modern aircraft since the Second World War, because that's what you need for jet engines. Another version of empiricism that we can see, and we can see in evidence and watch live on YouTube if we want to, is the current exploration of how to build a reusable rocket, which is what SpaceX are doing with their Starship. This is an example of the Starship. This is actually a successful experiment. They launched this rocket up 20 kilometers into the air, and then brought it back and nearly, but not quite, managed to land it. And you can see it nearly, but not quite successfully landing here. Trying things out and learning from our mistakes is how we make progress. It's how engineering always makes progress. And so if we are to adopt an engineering mindset, we must allow ourselves the freedom to make mistakes, but we must do that in a way where they're safe enough that we're not going to hurt anybody or destroy the reputation of our company. So we've got to be thoughtful about how we do that, and that's where the experimental work comes in as well. As well as all of those things, as well as our need to optimize for learning, we also need to optimize to manage the complexity of the systems that we build. Modern software systems are enormously, probably unparalleledly, if you can say that, complex. The picture labeled Amazon here is a picture of microservices in production. This is 2 or 3 years out of date, and it's not static like this. I once saw a movie of this diagram, and it's like looking at a living organism because it moves, it changes all of the time. There are services that are being retired and removed. There are new services that are being added constantly, and the relationships between the services change constantly. So this is complicated stuff. This is not easy stuff for us to deal with. So how do we deal with that complexity? Software development is about optimizing for learning and optimizing to manage complexity. We need to do both of those at the same time. So how do we manage complexity? And here's another 5 things, all of which you'll be familiar with. Once again, what I'm saying is not remember these things. What I'm saying is organize your work to always prefer these things. And those 5 things are modularity, cohesion, separation of concerns, abstraction, and coupling. So let's talk about each one of those. Modularity is, again, about organizing our work. And fundamentally, what we want is we want the ability to make change in one place without forcing that change elsewhere. So here's a modular system. We've got a module of engine and a module of aeroplane, and the aeroplane will be made up of many more modules. But to illustrate my point, if the flight entertainment system stops working inside the aeroplane, the engines don't stop working. They're working independently of the flight entertainment system, which is a good thing. But much of the software that we build often doesn't exhibit those kinds of properties. Another form of modularity is this. This is a modern iPhone taken to pieces. And a modern iPhone is a remarkable device in engineering terms. And the pieces are intimately designed to work with each other. But nevertheless, each piece is discrete and distinct and focused on solving one problem. So this is a modular design. An example a little bit closer to home is the idea of how we do printing. So when I first started programming, if you wanted to print something out on a printer, you had to encode in your application how to print on that specific printer that you were going to print to. There were no print drivers at that point. And so if I wanted to print something out on an Epson RX80, I had to write slightly different codes to the printer than if I was printing something out on an Epson FX80. That's how bad it was. Clearly, this isn't a great way of being able to scale up and build software and not worry too much about details everywhere. We had to know about the details everywhere. That added to the complexity of the systems and limited their flexibility. So at some point, operating system vendors and manufacturers came up with the idea of abstracting the idea of printing and then building modules behind those abstractions that we could plug in to translate between the abstraction and the detail of the individual printer that we're talking to. And we're all familiar with that kind of idea now. But that idea of modularity transforms our ability to gain flexibility in the system. Here's one more example of modularity. Here's some code. It's nasty code. And let's just have a look here at this if statement. Here's an if statement with 361 lines in it. The commonest bit of feedback that I get when I show people this if statement is, oh, we have much bigger if statements than that. That's not really my point, but still, it's fairly nasty. Here's the if statement in context of the rest of this function. It's not a nice function. It's big and complex. It's certainly not a modular system. We can improve this by simply moving the body of that if statement out. So here's the start of it. It says if unlikely bang CI, and then lots of stuff about structs. Everybody's clear about what's going on here, I hope. No? Well, fortunately for you, I did the work to try and figure it out. I think that what this code is really saying is something more like this. If there's no connection represented by CI, then create a connection. And that's it. So if we were to change the code to do that, simply moving out that block, we've made the code more modular, more tractable, more flexible. Now I could use that create function call perhaps in more than one place. Now it's easier to understand this code. It's easier to change this code, safer to change this code, maybe even easier to test this code as a result of this simple change by increasing the modularity. One of my favorite descriptions of software design comes from Kent Beck, who said, good design is about moving the things that are related closer together and the things that aren't related further apart. It's a bit jokey, but it's profoundly true, which is a hallmark of Kent Beck's things, I think. So we can think of modularity as the things that aren't related, moving the things that aren't related further apart, and cohesion as moving the things that are related closer together. We want the things that are related in our code to be in front of us when we're looking at the code, and all of them together so that we can understand what's going on, and that makes the code once again easier to change. Next in my list is separation of concerns. This is a slightly different kind of idea in that this is an idea that helps us to achieve the others, certainly in terms of modularity and cohesion. This is a modern electric BMW. And BMW, like lots of car manufacturers, electric car manufacturers, have made the decision to separate out the utility of the vehicle from the mechanical services that are needed to have a vehicle of any kind. So the battery system, the steering, the motors that drive the wheels, the brakes, all of those things are part of a platform. And if you buy an electric BMW, what you do is that you buy largely the same platform, which is then customized in different ways to be an estate car, a saloon, a sports car, or whatever other kind of vehicle that you're looking for. This is a separation of concerns idea applied to the design of cars, separating the utility from the practicalities of the platform that delivers steering and power and all of those things. Next in my list is another car and the idea of abstraction. This is actually my favorite car. It's such a beautiful machine. But one of the things that's kind of evident by looking at this is that there's not an awful lot of abstraction going on here. It's fairly clear what's going on. If you're of a mechanical mindset, you can kind of look at this picture and you can kind of figure out how it all works, really. So this thing here is, I think, a combination of accelerator and brake in one control. You push it forwards to go faster and you pull it back to slow down. This thing here that looks like a tiller is a tiller, and that's the steering mechanism. And you can almost see how that works. There's a handle on top on a tube, and a tube goes down, and there's a little push rod at the bottom of the tube that is connected to the front wheel. And then when you move the tiller, it rotates the tube, moves the crank, and pushes the push rod, which moves the steering wheel. You can see all of that very clearly and see how that works. But that didn't last for very long because it didn't scale very well in terms of our ability to learn to drive, to operate the cars, and to build the cars. So what started to happen is that the control system started to standardize a little bit around what we were doing. And over time, we started to abstract those controls further and further until we end up with something like this picture in the middle. This is a steering wheel from a modern car. And if you look at this, how does the steering here work? You can't tell. So maybe this is connected to some mechanical mechanism, so a parallelogram steering or rack and pinion steering, something like that. Maybe, though, it's power assisted, so it's connected to some kind of hydraulic mechanism. Or if it's a modern car, it might be more like a joystick on a computer where there's some kind of rheostat that measures movement as an electrical signal, which is then connected to via servo motors to mechanisms that can move the wheels and steer the car. So we've abstracted away the problem, and as a result, we can get in, we can use the controls and not care one jot about how those controls work. That's a powerful and useful idea. Let's put that into the context of software. Let's imagine two pieces of software that are having this conversation. So we're going to, the blue piece is going to initialize the orange piece, and then the orange piece is going to report it's initialized, and we're going to get a delivery date and get some VAT, calculated total for an order, order some items, and confirm that an order was placed, and so on and so on and so on. This is a pretty horribly, poorly abstracted design. This doesn't really, we can guess at what's going on here, but it doesn't really say what's going on very clearly. And if we wanted to stick to this design, then we know quite a lot of we can understand and are coupled to quite a lot of what's going on in the orange piece of software if we're the blue piece of software. None of that's good. So this is a bad design. What we could do instead is something more like this. We could say, we're going to raise the level of abstraction of the conversation. We're going to place an order and then confirm that the order has been placed. All of the rest of the detail is hidden behind those instructions and those communications. That's a much better design as a result. We want to identify points in the design where we can keep secrets. And we want really every interaction to represent some form of secret being kept. We don't want to expose all of the secrets of one piece of code to another. It's kind of the whole point of design, is to try and organize our code in ways that allow us to think about a problem and not worry about all of the details everywhere all of the time. Coupling is the last of my 5, and I did warn you that there'd be some Lego. So I am the very proud grandfather of 3 gorgeous children, and we have a lot of fun playing with Lego. And we have a Lego like the picture on the right, which is the kind of Lego that I certainly had when I was a little boy, a long time ago. And the amazing thing about this is that this is interestingly coupled. It's quite tightly coupled in respect to the way that the individual bricks plug together, but it's loosely coupled in the sense that we've got this very flexible way of organizing and assembling these bricks into whatever we like. So when I'm playing with my grandchildren, one of them can come up and say, "What do you like this, Grandpa?" And I say, "Oh yeah, it's wonderful, darling. What is it?" And they'll say, "It's a giraffe." And I'll say, "Oh, of course it's a giraffe. It's a brilliant giraffe." And they can do the same thing, whether it's a spaceship or a car or whatever else. The system on the right here is kind of almost infinitely flexible. We can build anything we like. We can use our imaginations then to understand what it is that this thing is that we've built. It's not going to be quite as elegant as the thing on the left. The thing on the left, though, has very different properties, and the coupling here is very different indeed. So to build the thing on the left, this is a model Ferrari. And if I wanted to build a model Maserati, I couldn't do that, even though they are similar cars in many respects. I couldn't do that with this kit because it only builds a model Ferrari. And in order to build that Ferrari, we've got to put the pieces into exactly the right place. So this is a much more tightly coupled system. Now, I can't say hand on heart that one of these is better than the other, because it depends. It depends what you want. If you want a Ferrari, the picture on the left is the best Ferrari of the two that you're going to get. I can build a Ferrari with the things on the right, but it's not going to look the same. It's not going to look as good. So if you want something that looks like the thing on the left, then you're going to have to put up with the inordinately expensive and challenging costs of tight coupling. If you want the thing on the right, if you can manage with the thing on the right, you have the flexibility to come up with a vast range of solutions from the pieces that you have. So managing coupling is a deeply important part of software development, and deciding where we are on this scale is important too. In general, my advice is to organize your work to manage the coupling with a preference towards looser coupling, because that's generally more flexible. Here's another example of coupling. So again, here's our two pieces of software. And let's imagine that the orange piece of software, that the team building that have decided to change the date format for the orange piece of software. So if you remember the first conversation that we had before, then we were getting the delivery date. So when we return the date in the new format, that's going to break the interaction with the blue one. And remember that we had a link through from the blue one to the database. So that's going to break the whole system. So that's not great. So if we have abstracted things, though, that reduces the coupling as well as giving us lots of other advantages. It means that we can do things like this. We can add a little translation point between the conversation. So when the blue piece of software talks in the version 1 conversation and places an order, the orange version can recognize that and say, I see that you're talking to me in version 1. So I'm going to translate the conversation into my internal version 2 format. This is what's called ports and adapters as a design approach, and gives us room to allow these two pieces of software to decouple them so that they each can change more independently of the other. So let's look now at applying those guidelines to something a bit more realistic. So I want you first to imagine using these things, managing complexity. Imagine building two systems. Imagine building one where there is no modularity, no cohesion, no separation of concerns, no abstraction, no coupling. That's common enough that you should be able to imagine that. It's common enough that it's even got a name. We call that a big ball of mud. But they're very common types of systems. Now imagine one where the system is modular, cohesive, good separation of concerns, divided up with good abstractions and minimal coupling. Which one would you prefer to work on? I guarantee you it's the second one. That's going to be a much easier place to work. So this is more than just motherhood and apple pie. These are tools that we should use and should apply to guide all of our work to build better software. Here's a little example. I'm rapidly running out of time, so I'm going to whiz through this quite quickly. Here's a car with a petrol engine. And when we start the car, we put it into neutral, we apply the brakes, and we start the engine. So let's write a test for that. Here's my test. We create a new car, we start the car, and then what are we going to assert? Well, we can't assert anything. So this isn't a very good car. So what I'm going to do now is I'm going to approach solving this problem from just one perspective, that is trying to make my car testable. I'm going to do nothing else. So let's start with a test, because that's the best way of making sure that the car is going to be testable. And I'm going to do what I often do in these circumstances. I'm going to write the test backwards. So what I want to be able to do in the end is say this. I want to say, well, the engine started successfully. That's my success criteria for this interaction. So I want to be able to do that. And I want to do that when the car has been started. And that means I need to build a better car like this. I need to build a better car with an engine that I've got access to. And in this case, all I need is a fake engine. I don't need a real engine in order to be able to test this. So here's what my fake engine would look like. It would support the ability of me to question whether the engine had been started successfully or not. Unless start was called, it hasn't started successfully. And there's my test again. So this has had a significant impact on the design of my code. And yes, all I'm talking about here is dependency injection. But let's think about what the implications of that are. So by injecting the engine into the better car, we have decoupled it. We have increased the level of abstraction. We've increased the modularity. We've increased the separation of concerns, and we've improved the cohesion. This piece of code is more about the car and less about engines. Previously, the other car needed to understand how to create a petrol engine and so on. So this is just fundamentally better code. And when we kind of put this into practice in production, what do we get? Well, we can first of all create exactly the same car that we had before. We can have a better car with a petrol engine, and now it behaves exactly as before, except it's more testable and more modular, more cohesive, better separation of concerns, more abstract, and reduced coupling. And if we want to now, as a result of those changes, we could create a better car with an electric engine without changing the better car at all. Or if we were crazy, we could create a better car with a jet engine, once again, without changing the better car in any way. So this is just better code. There seems to me little room for argument about this. By striving to make it more testable, we've amplified the properties that we value as properties that allow us to manage the complexity of the systems that we build, and resulted in this more flexible code that we can use in a wider variety of situations. So I'm going to ask you now to once again try the little thought experiment. I've asked you about managing complexity. Let's think about optimizing for learning. Let's imagine that once again we've got two different versions of the same system. So in one, there's no iteration, no feedback, no incremental working, no experimental working, no empirical discovery. So basically what that means is that we've got to think very hard, come up with all of the problems that we're likely to face, solve those problems, and come up with a perfect solution for how the system's going to work. And then we've got to execute that solution, that plan to build that solution perfectly, and then everything will be fine, right? Or we could work it iteratively. We could try something out, see how it worked by capturing the feedback. We could build systems over lots of those little tiny experiments, trying things out, seeing how they work, and moving on. And then we could monitor what was going on in production to see whether we got it right. And if we haven't, we can correct it. Which one of those is going to be the better way of building a complex system? Once again, I'm pretty confident that you would agree with me that the second approach is going to work better. And I'd like to point out in that both of those thought experiments, I said nothing about technology. I said nothing about frameworks. I said nothing about the nature of the problem that we're solving. This is completely generic for software development. This is how we build better systems. So fundamentally, what all of this boils down to, I think, is one underlying reason. They allow us to change our software more easily. The idea here is that if we're going to work in this more powerful way of incrementally growing our systems and tending them, we need to embrace change. We need to be able to cope with the fact that we're going to get some of this stuff wrong and we're going to need to correct it. Or even if we don't get stuff wrong, the situation will change and we'll need to learn from that. Or even if that doesn't happen, then we're going to learn how better to serve our customers. All of these things are going to be changing all of the time. That's just a truth of the world. That's not something that's weird to us or that meaning that we're not doing a good job. It's just how things work. So if there's one idea that I would like to leave you with at the conclusion of my talk, it's this. The quality of a system is defined by our ability to change it. Sure, we want our systems to be secure, resilient, all of those things, scalable, whatever else. But how do we get those other than being perfect before we start, other than working in ways that allow us to change the code, by able to try stuff out, see what works, and correct the things that don't. Thank you very much. That's the end of my talk, and I hope there's just enough time for a question or two.
Yes, so we have a few questions. Let's see. The first question. So feedback, experimentation, and empiricism are hallmarks of good lean product development. How do engineering teams collaborate with a wider product organization?
So I think that when you start to think in these terms, it starts to tell us something about that. I'm a very strong believer in agile approaches to software development and the kind of what I think of as the hyper agile approach to software development, that is continuous delivery. And if we want to be able to work in this way, where we can work as a series of small experiments, then the very product ideas are experiments too. And so we need to have close interaction with the people that understand the problem that we're trying to solve. We need to understand it well enough from those people, and then we need the freedom to be able to choose how to solve it. And there ought to be flexibility, to my mind, to be able to solve a problem as posed in the requirements process in a variety of different ways. We want the freedom to be able to try stuff out and to find better ways of solving problems. So I think that demands high levels of collaboration between all players, really, to achieve that flexibility.
Mm-hmm. Great points. Another question we also have about MVPs and startups. How to resolve the rigorous engineering process with a need for a quick startup MVP product. The rigorous process is slower to start something, although it's quicker later when things get complicated. Then there was a very long discussion in chat. And another follow-up comment was, isn't the purpose of MVP to experiment with the viability of a product idea? That's inherently experimental, so it's one step towards a more complex product. It's a fail-fast approach to new product development. So perhaps you could comment more about startups and MVPs and how we can use this in that context.
Yes, so I think that last post is on the money. I think that's absolutely correct. The whole idea here is to try, and I think of it as working experimentally, but an MVP is one form of experiment, surely. So ideally, what we're trying to do is that we're trying to find the quickest, cheapest way to learn a lesson, and the safest way. So how can we try out our ideas and see whether they're any good or not? Because often they are not. And so, yeah, I think that the original question kind of started out with the premise that what we're talking about when we're talking about engineering is some kind of heavyweight, overbearing process. And I think it can't be that. I think that that's once again, that's a category error. That's mistaking production manufacturing for engineering, and they're not the same things at all. So engineering is always, so if you think about somebody building, I don't know, a Mars rover, where do you start? You don't build the whole thing and send it to Mars and see if it works. You do a little experiment. You're probably going to start off by building a tiny little robot and seeing whether the wheels work on sand or something like that, or maybe a computer simulation. You're going to try and find out how to do a small, cheap, controlled experiment. That's all we're talking about. So start off with a small, cheap, controlled experiment and figure out what that is. That's what an MVP is, really. It's a small, cheap, controlled experiment.
Excellent. That's very useful for us to hear that. So I want to say thanks again, Dave. We learned a lot from you during this session about how to do software engineering in a modern way and learning from aviation industry and others. I would like to tell everyone here we have our upcoming session from Vlad, where we continue the discussion about coupling and software design and DDD. And here's an overview of the rest of our European sessions, USA sessions. Thanks a lot to our sponsors. And here are some further materials for your own learning. And feel free to join us on Meetup and follow us on social media. So thanks a lot, everyone, and see you at the next session. Bye.
Thank you. Bye.
Bye.